Let's get started. So to begin, this does not work because if you do that, you're gonna have this structure, right? This structure has that carbon right there has 5 bonds to it. That's more than the octet can handle. It's too many. And then for this one, this carbon right here, it basically looks like this with a hydrogen right here. There are no electrons right there that can move. So it's not possible for an arrow to start there. Next, this is just a definition. A Lewis base is donating electrons, and a Lewis acid is accepting electrons. So you can see that the N is giving its electrons right here, and it's sharing them with the aluminum. All right, and then for the next question, this is Ario. This is what we covered last week. So we look at the conjugate bases. We have this one, that's a conjugate base. And we have this one right here. That's also a conjugate base. And basically what you're looking for is which conjugate base is more stable. So we look at this one. This one has its charge on the oxygen. So does the other one. So the next thing you're going to look at is resonance. These can both do resonance. Right? Next thing you're going to look at is induction. This one doesn't have very much induction. I mean, it has that oxygen on top, but it's bound to a carbon, whereas this is bound to sulfur. So that means that side, that conjugate base is more stable. So that means its acid will be more acidic because a more stable conjugate base means a more acidic acid. So this side is more acidic. And as we learned last week, the equilibrium, it favors the side with the weaker acid. So this side is favored. Next, we're going to look at this molecule right here. So this right here, this oxygen, it has one bond, another bond, and then it has 2 lone pairs. And we know that because it has no formal charge. So as we learned previously, each bond is 1 point and each lone pair is 1 point. So we write this out. 1 point, 2 points, 3 points, 4 points. That comes from 1, 2, 3, 4. So that would be sp3, right? So that means that one is sp3. And its electron geometry is tetrahedral. But do we know the molecular geometry of that? Does anyone have an idea? What shape is that oxygen?
What was
What was
that?
that? It is bent. It's the old one.
Yeah, it's not.
All right, next we're looking at this oxygen right here. Again, same as the last one, 2 bonds and 2 lone pairs. So that's going to make it sp3. And that one is also tetrahedral. Some of you might be wondering, why can't it do this resonance right here? Typically, in an aromatic ring, it has conjugated pi bonds right there, there, and there. So those want to stay. Those are very, very stable. An aromatic ring is very stable. So to get rid of the aromaticity, it requires an immense amount of energy. It's probably not going to happen in resonance. Does anyone have an idea on what shape that oxygen is? Yes. Thank you. All right, same thing for this one. 2 lone pairs, 2 bonds, sp3. It's also bent. It's the same as the last two. Next, we're looking at this nitrogen right here. We know it has that lone pair right there because it has no formal charge. When nitrogen has no formal charge, it has 3 bonds and 1 lone pair. So again, that's going to be sp3. Does anyone know the shape of this one? What was it? Yes. Really? All right, next. This is just resonance. Okay. So, does anyone know the name of that first pattern? This one right here. Yes, that is an allylic lone pair. And this allylic lone pair can be repeated throughout the molecule, just like that. And then for the resonance, you draw dotted lines where bonds sometimes are and sometimes aren't. So we see that this bond is not always there because it's not there in this molecule. Same for this bond, it's not there in this molecule. And basically, how you draw that is you're just going to draw dotted lines everywhere there used to be a bond. And where there was a negative charge at one point, you use this symbol right here, just like that. Same thing for the positive. Okay. Going on, we're going to look at localized and delocalized electrons. So we're looking at these ones first. Did anyone put that they were delocalized?
Thumbs up for yes, thumbs down for no.
Did anyone write that this one was delocalized? You said it was delocalized?
I did.
Why?
Because can't you take the electrons on the nitrogen and do like an allylic lone pair, make a double bond,
Hmm.
and take the double bond.
So what you're saying is this,
Yeah, and
and then that?
Yeah.
Okay, well, that might be possible, but these electrons themselves, they are not participating in that pattern. They do not have any resonance possible with those. Next, we're going to look at these ones. Does anyone think you can do resonance with those? No? Okay, yeah, so that is localized. And these ones, does anyone know what resonance pattern those ones can do? Yes, thank you. So to summarize, if electrons can do resonance, they are delocalized. If they cannot do resonance, they are localized. Okay, that's the end of that.
Just by the way, the oxygen molecule in the previous example was sp2 according to Dr. Jesky. We have to correct that.
This one?
Yeah.
Okay, sorry, mistake. So this, let me zoom in. This one right here, this is actually sp2. So it can do resonance. Ignore what I said about not breaking the aromatic ring. That's more of an orgo 2 concept. So it can do an allylic lone pair right there and right there. So I'd make it sp2 because 1 point, 2 point, 3 points. You write this out. 1, 2, 3 makes it sp2. All right. So now we're going to cover material that is not necessarily on your quiz tomorrow. However, it will be on your exam next week. So it's good to learn this now because next week we're going to be conducting an exam review session. So we won't be covering this material in depth next week.